welcome everybody to week 2, day 1. We're going to be talking about the Zeta homework assignment and how to decompose programs today. Looking at the grades, it's about not as good as I had hoped. I'm not going to show the grades here. Unfortunately, there's a lot of zeros on that. So, nothing in this assignment required any sort of knowledge beyond halfway through CSI 40, but it's like a loop inside of a loop inside of a loop. In that mental skill, you need to, that's a muscle you need to develop in computer science. You have to be able to look at a problem and be like, all right, how do I break this down? And there's two general approaches to doing this. I give a lecture on this in 40. Let me unlock the chat channel. Lock down. There's two general approaches towards doing this. There's top down and there's bottom up. So for the Zeta assignment, you have to do a summation of the results of a function. And that function counts all the primes from the number 0 to the number passed in, basically. So where to begin? First way to begin is you might write a function to determine if a number is prime, right? And then that would be a bottom up, because that's the lowest level function you need to write. You first need to write a function that checks to see if a number is prime. You zoom up a level and write the prime counting function. The prime counting function counts all the numbers, how many primes there are up to x. And then you zoom out and write the summation that calls the prime counting function multiple times. And then you zoom out and write main. Okay? That's one way you can do it. Or you do it the other way around. And I'll do it the other way around just because I feel like a lot of people started with the is prime function and then didn't even consider doing it in a top-down fashion. So let me just pull up the equation for this homework assignment over here. And anyone have any? Yeah, it's being collected right now. So I'm feeling fine. I'm gonna get a COVID test tomorrow and see how that works out. I can't go back to campus until HR clears me, and HR themselves are affected by COVID. So we're gonna be online for the time being. I expect. Actually, I don't know what I expect. It really depends on the results of the test and how long it takes HR to get back to me. Okay, so here is the thing. Here is the thing that you have to implement. Just that. That's the homework assignment. A little bit of error checking. Make sure I is less than or equal to j, and I and j must both be greater than or equal to 2. And that's all in the README. So it's important to get into the habit of reading the README very carefully, especially when I have like an errors section that talks about what kinds of inputs are not allowed, so you can't type in a negative number, right? Not that there's anything wrong with it. It's just it doesn't make any sense to, what's the prime counting function of -5? Like, it's sort of nonsensical to me. So I just sort of said, nah, all that's off limits. Throw an error if that happens. Okay, so let's do it from the top. This is our notes from last time. By the way, all the notes from last time are up on the public directory. I posted the link to it in the chat channel. Okay, so in main, like this, and if we're going to do top down, then we're going to start at the highest level, which is the summation. Okay, so int I equals read. Please enter I. I don't remember exactly what the syntax is. Please enter j. So we're going to read an I and j. We'll do a little bit of error checking, and actually I'm going to call this one I just because when I make for loops I like using I. So I don't know. Coming up with a better variable name than that, I don't know. Can't help you. That's the hardest thing in computer science. And then we're going to make a die function. yeah, bad input, and exit with exit failure. Okay. So if II is less than Q, or J is less than 2, or J is less than I, then die. So that handles our error checking for the assignment. I. So confusing. Okay. So that is our error checking and our input. Squirrel's a possibility. Not going to handle that right now. So for equals from and I equals II to I is less than or equal to J. So this is the summation we're doing here. I plus plus. So we're doing this giant sigma, right? Sigma means add up all of the numbers in this series. And so like if we put in 2 to 5, it would add up the results of pi of 2, pi of 3, pi of 4, and pi of 5 together, and then return the result. So we need to do a sum, and sum equals 0. And then we're going to say sum plus equals the pi of I. So that is, yeah, pi doesn't exist yet. Okay. And then we will say the answer is do sum. And that's how I would begin if I was going to be doing top-down decomposition. Decomposition means how you break the problem down. And that's really what the exercise was on this assignment. And there's actually a secret goal of this assignment, which is that this assignment is not actually solved this way if you want to do it correctly. If you want to do it the best way. You actually don't solve it this way at all. Okay. I wouldn't write SM2 for sum. I would make your variable names more readable than that. Yeah. You might be looking at I and J with askance. But I is, if you ever see I in code, it's going to be a loop counter, you know? Like, we all know what I means. Just, why I don't know. Somebody did it back in the 70s, and we've all copied him or her ever since. Okay. So now we need to go down a level. So we need to do pi of I. But before we do this, we're gonna test our code. So I'm just gonna make what's called a stub function, and it's just gonna return 1. Because you might be like, well, how can you test your code if the lower level doesn't exist yet? So what you do is you make a stub, and so this is gonna return, yeah, it's a pi, it's a prime, or the number of primes less than x is 1, whatever. I can make this any number I want. It's just there. It's just there so that the code compiles. I do care about style, actually, Mincorelli. I don't grade you on style. There's an important difference. I don't grade you on style, but style actually is kind of important. So let's say from 1 to 1, bad input. From 2 to 1, bad input. From -1 to 5, bad input, good, that's all working. From 5 to 3, bad input, cool. Okay, so from 10 to 20, the answer is 11. And so that is correct, and in fact, that's a reason why I picked 1, because there are in fact 11 numbers from 10 to 20. I wanted to make sure that my loop is working correctly, that it's running the correct number of times, because whenever I have a non-standard for loop, I always double check and make sure that the for loop is actually running the number of times that I think it is. Might even try it from like 2 to 5, and then I count on my fingers. 2, 3, 4, 5, 4. Okay. And I literally do. Like, I just start with like, something I can count on my fingers, because I never have any confidence that a for loop is going to run the correct number of times whenever I don't follow the pattern. Okay. I always double check. Yeah. Amanda's in your rating. Yeah, you're absolutely right. You're absolutely right. I don't grade you based on your style. Your grades are based on correctness, because that's how it works in real life. In real life, I don't care that much about... I shouldn't say that. In real life, correctness is king. Having code that works correctly is king. And last year I had a student ask me, like, why do you not give partial credit? I mean, I worked really hard on this assignment and it doesn't compile, but you know, why don't you give me like partial credit for it? And the answer is because like if you work for a company and you can't even get your code to compile, that is worth 0 to the company. You know what I mean? Like you can't even compile it, you can't even test it. Like no, like you go home at the end of the day and there's nothing for the QA team to even work with because it won't compile. That is literally worthless to the company. They're paying you money and you can't even make it compile. So, yeah, that's why the grading system is the way that it is. And in fact, it's quite literally based on how many test cases you pass, because that is the value of a program, is how many test cases it passes. You know what I mean? So the more test cases you pass, the more work you've done. And it's a non-linear relationship, right? Like you'll start off at 0 test cases for a long time and then jump up to like 7 or 8 or 9, and then you kind of work on the last couple, and that's literally how it works in real life. So Apple might pay you for stuff. Okay, so yeah, and so the grading system is based literally on how real life works. Yeah, so kind of, because companies actually do care about style, and they'll oftentimes enforce style guidelines automatically. Like they'll actually have their code check your code for style and make sure your formatting is correct and things like that too. But okay. Okay, so now let's drop down a level and go into the pi function. So the pi function is going to count how many primes there are from 0 to x. Okay, so there aren't any primes at 0 or 1, so this function here is going to be sum equals 0 for int I equals 2, I is less than or equal to x, I plus plus. So, because 0 and 1 aren't primes, so we'll just start at 2. And I will say if is prime x sum plus plus, and return sum. And so this is the next level down. So the prime counting function is just going to count how many primes there are less than or equal to x. And there is no is prime function yet, right? That's why it's flagging it. So I need to stub that one out. This is not a stub anymore, but let's make a new stub. Int is bool is prime x. Okay, and now it's going to, and we'll just say yes, everything is prime. Everything's prime. Yep. And notice the name, the variable name. Oftentimes I don't know what a variable name is going to be, so I just kind of give it a name. And then after I start writing the code, I realize kind of in my head, no, that this is what the name needs to be. And then I have to go back and change it. It's actually kind of how I go about naming variables. Like I'll be like goals scored, and then later on it might become score goal or something. Just in my head, like when I'm writing the code and using it, score goal just makes sense. That's how I remember it. So I actually go back and change the original name to match how I think it should be used. Okay, so now if we want to test it, we could write a function to just call pi itself, but we can actually just call pi itself by just calling it one time. So if I, and j are the same, it'll call p one time. So we make it from 10 to 10, and we say it is giving us an answer of 9. Is that correct? 2, 3, 4. I should have picked a smaller number. Yep. 5 to 5. Okay, so 2, 3, 4, 5. Okay, 4. Good. So the prime counting function is counting every number from 2 to x as prime right now. And it's giving the correct answer. So let's try a couple more. Okay, 5, 6. Okay. Now we just need to write a function to see if a number is prime. And we can do that with another for loop. So we got loops inside of loops inside of loops. And if you try writing them all at once, your brain's going to lock up. You have to decompose a problem systematically. Okay? That's the whole point of the Zeta assignment, is your ability to split a program into its component parts, because none of these things are beyond your grasp, right? The number theory is beyond your grasp. It's beyond maybe it's not beyond your grasp. I am not an abstract number theory person. I have no idea, you know, anything about zeta functions or whatever, but I can, when I was looking through the thing trying to figure it out, I was like, this my students can code. And looking at their test results, it's not too bad, not too bad. I think Carly's code is seg faulting though. So let's write an is prime function. So for is 2, I is less than or equal to x, I plus plus. So we're going to check to see if and this doesn't need to be x, it can actually be the square root of x. Because like if you want to see if 100 is a prime number, you actually don't need to check higher than 10. Because, yeah, but if that's kind of beyond you, let's just do x over 2. Okay, so if I can get it to not seg fault, it'd be faster than mine. Maybe. I could probably tweak mine a little more for speed too. All right, so okay, so how do we check for divisibility? We're now kind of at the bottom level here. So if that number divided by I is equal to 0, this means x is divisible by I, therefore not prime. Because a prime number is only divisible by 1 and itself. And that's why we're starting at 2, so we don't do a division by 1. And we stop below x, so that it never divides by x. So if we ever find an even divisor, then we know this is not prime. We make it through that whole loop, it is prime. And that is Zeta. That's the whole assignment. Yep, so if you know how to decompose problems, it's 15 minutes of work. And then I'd have to run the input tester and make sure that the strings line up and things like that. Like I don't remember what the exact strings are and stuff like that. Am I recording this? I sure hope so. Yes. Yes, I am. Yeah. So, how do you make it faster? What about the Miller-Robin test? Okay. So, before we get to that, do you have any questions about this process of sort of systematically breaking a problem down? This is top-down coding, where you have stub functions kind of being like, yes, it's prime. It's not. But, yeah, sure, it's prime. And you just have these, mock functions that just be like, yeah, the number of primes less than 10 is 7. It's wrong, but it gives you a number that you can work with. And then you can test each level of code as you go down. Oh, I understood that the assignment of the looping may be second guess everything. Yeah, it's a loop within a loop within a loop. So this is actually a really horrible running time. Okay, if I were to run this, here, let's test it actually. From 2 to 2, there's 1 prime number at 2. There's 2 prime numbers by 3. 4 prime numbers by 5. That's not correct. 5. 2, 3, 4. All right, let's test this. For int I equals 0, I is less than or equal to 10, I plus plus, see out, I is prime, is prime. So let's see if there's an error in my is prime function. 2, 3, and 5. Yeah. No, that's correct. So maybe, why am I getting from 5 to 5? There's 4? It should be 3. Okay, let's test the code some more. So this should go from 2 to 5, right? X. That's why. I. Always test your code. 5 is 3. There you go. All right. Always test your code more thoroughly than I did. Okay. That's better. So, yeah, it's an order n cubed problem. So basically, if you do it for a small number like that, it's fine. If you do it for a million, 100,000, let's just do 100,000. Runs forever, right? Okay. Runs forever. So, in your hints, there's some hints for making the code faster. So there's a couple things you need to do to pass test cases 9 and 10. First of all, they were too big to fit into either a int or a long, and so you have to use something called a CPP int, which allows you to make much bigger numbers than ints or longs. They're essentially infinite precision ints. And yeah, so that's how you get your numbers not to overflow. For one thing, you just use CPP ints, and you might be like, but these different functions don't work with it. Yeah, and so you'd have to like look up the documentation on CPP ints and like try to figure out how do I make a square root on a CPP int or whatever. Okay. That's why the last 2 are extra credits, to see if you can figure out how to read documentation and figure stuff out. So the Miller-Robin test is a faster version of is prime. Okay. It's nice until you create those areas where it doesn't know how to plus equal something. Yeah, it's different, and then you need to figure it out and look at the documentation and not start the night before and all that kind of stuff. So the Miller-Robin test. So if you wanted to use it, you could go into Boost Miller-Robin, and so you want to make a faster is prime function. Come in here, and they have an example right here of how to see if a number is prime or not. And this will see if a number is prime in 25 operations, not a lot. So that is how you do it. Okay. You tried implementing it, you could, I guess, but it's already done for you. So why implement it? It's faster to just look up the documentation, make that call to Miller-Robin, and then that replaces your isPrime function. And it's much faster. It's order 1. It's 25 steps instead of x, where x is the size of the integer. So if you're working on numbers in the 100 billion trillion range, like, you don't want to use your isPrime function. Okay. So I said, get your code working correctly for the base test cases and then rewrite to optimize. And so the first thing you can do to optimize is that's not a stub anymore. To do replace this function with a call to Miller-Robin. So Miller-Robin can actually determine if a number is prime without factoring it. Okay, so which is kind of mind-blowing. It can know that a number is composite, like 15 is a composite number, right? It's 5 times 3. It can know that 15 is composite without actually knowing what the factors are, which is a really cool thing. And you'll learn more about that in CSI 26. Yeah, it would probably be prime. Now, the odds that it's not prime, and I actually tested this against the known quantities. Like, I actually ran it for a really long time to make sure it didn't have any errors in it. see, Miller-Robin is 75% accurate. And so it's not perfectly accurate. And so if you do one trial with Miller-Robin, you have a 75% chance of being correct, right? Well, it's 100% if it's composite, it's 75% if it's prime. And so that means the odds that it's wrong are 25%. And so that's why we do 25 trials. That means the odds of it being wrong are 1 out of 10 to the 16th power. Okay? It's minuscule. And you can increase the number of trials if you want. Okay? So, yeah. So you replace it with Miller-Robin. Now your code is much, much faster. If you're doing a million numbers, it'll be a million times faster because you don't have this for loop anymore. Okay. One trial, I wouldn't do one trial. One trial, you're going to be wrong a quarter of the time, right? And so your count's just going to all get screwed up. But if you do 25 trials, the odds of you being wrong are 1 out of 10 to the 16th power. It's pretty small. And you can just increase that number too if you want, if you're worried about it. I did. I increased the number of trials to like 50, which makes it incredibly minuscule that you're wrong, and then generated the test cases, and then did it again with 25 trials, and it was correct. So the grades are already posted for Zeta. Check your grade with Alpine. So type Alpine, and it'll tell you your grades. Message index. Okay, so what else could you do to make the code faster? You could see one of the things about this is that you are going to be repeating work over and over again. For example, if you do the prime counting function for 5 and you do the prime counting function for 6, there's a really important observation here, which is that you don't need to do all that work again, right? You don't need to count all the primes from 1 to 5 again when you're doing the prime counting function of 6, pi of 6. All you need to do is see if 6 is prime. That's it. So you just remember your results from the previous computation and then just see if 6 is prime. If it's not, which it's not, just return the same result as last time. So my function only has a single for loop in it. I'm not going to show it to you, but it only has a single function, a single for loop in it. It just starts at the beginning number, determines how many primes there are up to that point, and then for the next one, it doesn't call the prime counting function again. It just sees if the next number is prime or not. If it is, the number of primes goes up by 1. If it's not, it stays the same. And then it just sums up all of those numbers as it finds more primes. That's why my assignment's so fast. My implementation's so fast. And in order to start for the first one, I use the hints file. CD Zeta hints. These are good starting places. So the prime counting function has already been computed for you at every power of 10. So if you're doing like 100 billion or whatever to 100 billion and 100,000, you can actually start with this as your starting point, and then you just as you're going from 100 billion to 100 billion and 100,000, you pull. I don't know which row is 100 billion, but you pull that number out, and then you just loop one time from 100 billion to 100 billion and 100,000, and every time you find a new prime, it goes up by 1. You just add all those numbers together. So it's a very fast for loop, singly nested for loop, order in. Yep. Type I to go to your inbox, and then it'll tell you what your grade is. Or you can wait till after class, and I'll put them all up on campus. So that is no. So that is that's why the hints array is there, so that you don't need to compute the prime counting function below any power of 10. Okay. So if you're going to compute the prime counting function from 2 billion to 3 billion, you would start with all the numbers up to 1 billion computed for you, and then you would have to count up to 2 billion and then count from 2 billion to 3 billion. It still wouldn't be that fast, but it's pretty fast. and that is Zeta. So, okay. So we are now moving into a new subject. In fact, I'm going to stop the recording here. I'm going to actually upload this lecture in two parts. The first part is going to be how to decompose a function, and then the next one will be on our new topic, which is object-oriented programming. So let me stop the recording here.